Good morning and welcome to our second session on evaporation. At this stage, after attending to our first or our previous session, you are expected to be able to define evaporation. You are supposed to be able to tell the difference between evaporation, distillation, drying, crystallization. We discussed previously the major part which compose an evaporator. And you are also expected to be able to name some examples of applications involving evaporation in chemical engineering. In this session, let us start with the different types of evaporators. As you can see on our slide number 6, which is in front of you, we listed 5 different types of evaporators, the modes of agitation used in those evaporators, as well as the applications for each type of evaporator. We have what we call horizontal tube evaporator, short vertical tube evaporator, long vertical tube evaporator, forced circulation evaporators, of which um, uh, a sketch is presented to you here. As you can recall, all the 3 major parts uh, of an evaporator are represented. You have the liquid mover, which is a pump, which allows to convey the feed to the heat exchanger, and you have finally, the vapor space. Now, in the falling film evaporator, no pump is used. They take advantage of gravity, and you can view a falling film evaporator in our chemical engineering lab. Now, how do you characterize the performance of your evaporator? How do you tell whether evaporator is being undertaken properly? There are 2 measures of the performance of an evaporator. The first one is what we call capacity. By capacity, we mean the amount of solvent which is evaporated per hour. One will tell you, for example, that we are using on our plant a 500 kilograms per second evaporator. 500 kilograms per second in that case means what is being evaporated, the solvent which is being evaporated. Unlike in other applications, when, for example, they give you the capacity as being the output of your process, of your plant, here the focus when we define capacity is on the amount of solvent that we are evaporating. The solvent can be water, for example. The second important measure of an evaporator performance is the economy. By economy, we mean the amount of water that you are removing, that you are evaporating, or in general, the amount of solvent which is evaporated for each kilogram, for each unit mass of the steam that we are using, or of any service stream that is used for, let's say, evaporating. You can see those 2 equations providing you means to calculate capacity. Capacity will be the flow rate here of the evaporated uh, solvent. If MF is the flow rate of the feed and M is the flow rate of the concentrate or the liquor, then through material balances, you'll find out that the flow rate here will be mf minus m. Now, when you divide this flow rate by the flow rate of your steam, the flow rate of steam there, you find what we call the economy. Let us look now at the evaporator model. I'm going to present to you shortly an arsenal of equations which can be used to analyze and even to design an evaporator. Some students among you had already that opportunity of studying in S3 or S4, but since you have the right to forget, I'm going to refresh your mind. Now, there are some assumptions which one has to bear in mind when using the set of equations that will be presented to you. So the key assumption in formulating the model that we are going to see are as follows. First, the feed is assumed to have only one volatile component. Only the latent heat of vaporization of steam at Ts is available for heating and vaporizing the solution. The boiling action on the heat exchanger surfaces agitates the solution in the evaporator sufficiently to achieve perfect mixing. So you assume that there is perfect mixing. Uh, so the solution temperature equals the exiting temperature of the thick liquor concentrate. Now, what is meant by that assumption number three? Assumption number three only tells you that there is equilibrium, thermodynamic equilibrium, which is achieved in your evaporator. It means the temperature of your solvent. Let me go back to that figure on slide number 7. It means that the temperature of this stream, of the evaporated stream, is the same as the temperature in the vapor phase, is the same as the temperature in the liquid phase. Assumption 4, the overall temperature driving force for heat transfer can be calculated as the temperature of your steam minus the temperature of the product. Now, 5, the driving force is high enough to achieve nucleate boiling, but not so high to cause undesirable film boiling. So we assume that there is just, there is nucleate boiling being achieved there. 6, the exiting vapor temperature is equal to the evaporator vapor space pressure, or rather the exiting vapor temperature, TV, correspond to evaporator vapor space pressure, which implies that you can use your steam table, knowing the pressure, to estimate what will be the temperature of the vapor space. No heat is lost from the evaporator. Now, here is the set of equations that we are going to use for analyzing our evaporator. I'll give you a few minutes, 1 or 2 minutes, to have a look at that set of equation. You have equation for mass balance, for energy balance, and heat transfer rate. This ends our session 2. Thank you.